170. I've probably said something about this before last week, right? But like, there's just something already awkward enough in class, in person, and this sort of minute and a half or what I have, 77 seconds right now of like just talking. It's a little extra. It's just a little next level extra when I have a camera on and you all don't. So, you know, we'll just. Okay, with about 20 seconds, I will just maybe do some non-class announcements and just say, if you're a Wisconsin resident, there's an election tomorrow, so please make your voice heard. And please complete the census. I just noticed when I signed into Canvas this morning that there was a post about how if you're on campus, if you were on campus before spring break, that is, that campus is actually submitting some information to the census on your behalf. I think more information is probably forthcoming about what's going on there. So if I find out anything, I'll let you know. It's important to be counted as far as resources for the region and state, that kind of thing. So let's see. Yeah, let me move this over. I already started recording. Okay, yep. Oh, and then for the quote, I mean, you all know Bill Withers passed away last week, right? So I thought this is a good song. You know this song, I hope. I felt like the lyrics were good at this time, so yeah. Maybe play the song later today. Okay, let's do a round of announcements. I think there's plenty to say. The exam that's technically scheduled for Thursday goes up to what we did in class last Thursday. I meant to say that at the end of class last Thursday and just forgot to mention that. I also noticed I was going to post a curve sketching summary handout thing. I said I would do it on Wednesday, and it wasn't there. so I did it on Thursday, but you'll find that in Canvas. Practice Exam 3 stuff is available. And I just this morning posted an Exam 3 info PDF. The quiz for Tuesday, slightly different format. It came up from some students that, it would be much easier if we could submit a picture instead. I will say that had occurred to me last week. And the reason that I didn't have it in that format was I didn't want to make the assumption that everybody had a way to do that. Like, I didn't want to assume everybody had a phone. And I know that may seem a little extreme, but I just, equity kind of things. I'm trying to think about these things, but I realized here's a way that can sort of be best of both worlds. So I hope you'll work with me on this. And sorry about the new format. I'd like you to turn in a picture. So if you do have a phone and you'd like to write down an answer to a quiz on paper and then take a picture of that and upload that in Canvas, that works. If, on the other hand, that's not what you would prefer, you can still type, as I was encouraging last week. What you would do then is type your answer and then take a screenshot of that. So I did post some instructions on taking a screenshot in both Mac and in Windows. So on some level that will hopefully be a best of both worlds. So it just creates a little more flexibility for you in terms of you can now do that. But if you prefer to just type and then take a screenshot, that'll work. Just reminder also that the day before a scheduled exam, there is the Math as a Process. So a pre-exam 3 assignment. So it's meant to be a short thing where you just kind of go through and say, these are the things I think that are on the exam, and here are the things that I want to work on before the exam. And then Thursday itself is officially the date of the exam. That said, I recognize that schedules are different for people. Some of you all are working in essential jobs, and I don't want to. I guess the point is I don't want to assume that everybody can be here at exactly this time and take the exam. So here's what I would like to do. Is there's this 48-hour window. Sorry, it says after here. What I meant to say is after midnight on April 9th. So you can start the exam as soon as midnight on April 9th, but the final time to turn it in is at the end of the day on April 10th. Now, that's a 48-hour window of time, but you do not have all 48 hours to do the exam. So what I'm trying to do is create a bit of flexibility where it's like you can, if you want to do the exam on April 9th, cool. If you want to do the exam on April 10th, fine. You can't work on it like both days. What I'm trying to say is, trying to recognize different schedules. If you don't want to work on it Thursday, you're busy, you've got work, then work on the exam Friday. Or maybe you don't feel comfortable yet taking the exam on Thursday. So this creates a little more flexibility too. You can look at the practice material and say, I'll do the exam on Friday instead. What I've done, though, within this 48-hour window of time when the exam is available, you have 5 hours to complete it, meaning you go into Canvas and then you click Start, and then from the moment you click Start, you'll see all the questions, and then I want you to only really spend 55 minutes, an hour, or if you want to spend a little more, an hour and a half or something like that, fine. I'm not policing that, but the whole point isn't to take all 5 hours to do the exam. You've got other things going on in your life. I'm sure you're busy with other things. The whole point is I want you to just take an hour or an hour and a half to work out the questions. And then all this extra time is really just meant so that nobody stresses, hopefully, about the process of creating the pictures and uploading those, which that process ought not take too long either. There's a practice version of that, and it's formatted essentially just like the quizzes. So I hope that's going to work. Again, the point is you don't have all 48 hours. It's just within this 48-hour period, you got to choose a 5-hour block of time to work on this thing. I do want to make sure that this is clear, and I say it's all in Canvas, but I think right now it's maybe a little extra important for me to demonstrate some of these things. So I've logged into Canvas just to show you on screen here. Of course, this is part of the recording as well. And within this magenta e-color, that's how Canvas simulates me pretending to be a student in here. So if you click in the quizzes section, I'll just give it a minute to load. So there's this new practice quiz, and it doesn't count for credit whether you do it or not. I would encourage you to just do it. I'm not going to actually grade this new practice quiz. It's there again because of the slight change in format of uploading a picture. So just look at the question. It's meant to be an easy math question. I think it's just take the derivative of x cubed. I forget. Just something like that, right? Just to just to practice the format again, because the format has changed. The whole picture thing. And then sometime during the day tomorrow, you do quiz 13. It's in the same general format. So I basically created the new practice quiz and created quiz 13 at the same time. I created them in the same way. It's just that the actual questions being asked are different. Once everybody, so quiz 13, sometime during the day on Tuesday. It's due at 11:59 p.m. So sometime after 11:59 p.m. on Tuesday the 7th, so probably Wednesday morning, I'm just going to delete this new practice quiz. So I don't care what you turn in. I'm not even going to look at it. It's there to practice the format. Same deal for the exam on Thursday. Sometime prior to that, you might just want to like try the practice exam format thing here. Again, same deal. This is ungraded. It's there so that you can get used to the format of things. So the questions are the same as for the paper practice exam. If I go to the assignments area, just to make sure we're all on the same page, to point out some things, we'll give this a moment to load. By default, I think Canvas shows things by date, which has its convenience. I tend to prefer by type, so that all the quizzes are next to each other. Excuse me. So again, you'll find a link to the same new practice quiz. And you'll find quiz 13 here, which is available all day tomorrow. I think you get a 1 hour time window to complete it, but it's anytime during the day tomorrow, you can use that 1 hour time window. And then, this is not good. I think my mouse froze. Okay. Yep. Sorry about that. Computer's slow. Can everybody still hear me? Before I talk, can I just get at least one person in the chat to post a...
Hear you.
Okay. Thank you. All right. Good. Because I don't want to assume... Yeah. All right. Whew. Okay. And then same, if you scroll down a little further in the in-class exam sections, you'll find the practice exam format. There's just the format, like again, an ungraded thing. If you click here, there's going to be another link later in the week. I just haven't had a chance to make the actual exam yet. But if you click on exam 3, this is where, just like if you would have clicked on exam 2, you'll find all of the usual things here. So all the resources to study, the compare, contrast, find the error. You'll find here the links for the practice exam and the practice exam key in the usual paper format. And then I just posted it this morning, but you'll find an exam 3 info page. So this, just like in previous exams, it's trying to clarify what's being covered. And again, just to say it right now, it's up to what we did last Thursday. But the other thing about this is it tries to clarify this time frame. Like you've got a 5-hour window within the 48 hours to complete. I should comment that the reason it's only a 48-hour time frame is I need some time to do some amount of the grading. I don't even anticipate if you all have to turn it in by the end of the day on Friday. That gives me Saturday and Sunday. I don't think, just with the new format as well, I don't know that I'm going to be able to grade all of it, even over the weekend, even in just that time. But like, it's my chance to get a chance to do it, because I just know from this week, like during the middle of the week, it just doesn't, it's not likely to happen. So I hope that strikes a decent balance for that. Okay. Here's where we are so far. So we've looked at local maxes and mins. And just as a brief review and summary, a local max is a point in the graph that is higher than all the nearby points. And similarly for a local min, all the points in the graph that are lower than all nearby points. That's what we've done. Like a local max is like, where's a balloon going to get stuck? But now we're going to change things up just ever so slightly. Here's a new thing. We're looking at this thing called an absolute max. I'll abbreviate that abs max at times. The wording is just ever slightly different. I changed the nearby to the word all. Yeah, an absolute max is a point in the graph that is higher than all points. And of course, similar idea for absolute min, right? It's a point that's lower than all points. So what's this nearby points versus all points difference? It's like, think about like what we used to do with a local max. I'll just stick to maxes because the min's same general story, right? So let's think about local max. The local maxes are like, where is there the top of a hill? Where is there the top of another hill? And then absolute max is like, okay, you've got a bunch of hills. Where's the tallest hill? That's the difference. So I'd like to demonstrate just from the following picture in Desmos. In the picture that we're about to look at, I've already pulled it up so that we don't have to wait for loading time. You will see 3 local maxes, and one of those local maxes is going to be an absolute max. So let me move one tab over here. So the function, don't worry, it's x cubed minus x to the 4, whatever it is, it doesn't matter. But here's this function, and the function I defined actually has this domain issue of like, you start at x is -1.5-ish, but whatever. The point is, if you just look at the picture, stare at the picture, there are 3 humps, right? There are 3 peaks, and all 3 of these are local maxes. 2 of these are local maxes only, and I've labeled them in purple. They're these are 2 places where balloons get stuck if you were to drop from let go of a balloon from below. This point that's labeled in orange is also a local max. That's a place where a balloon gets stuck. But the key thing is that this is the absolute maximum, also called the global maximum. It is the point that is highest. It's the largest y value amongst all the points. And so that's the difference. We're going to look at some pictures, and let me go back to the slides. What we're going to do today, just to outline it real quick, is we're going to look at pictures for a moment first. We're going to look at the graphs. Not that I'm expecting you to graph here. You learned last week that the process of graphing a function using all of our new calculus stuff on top of algebra stuff can be rather tedious. The goal right now in looking at pictures, I don't want you to tune out. We are looking at pictures right now to help explore what the procedure looks like. And I think it's important to do that. If you just try to memorize a procedure on its own, it's just a little too painful. So I tried to just preview so far what, in a nutshell, absolute max is. Now here's a more thorough definition. So absolute max or global max, what is it? So first of all, you're given a function, y equals f of x. You're also typically given a closed interval. So from x equals a to x equals b, and bracket, meaning including a and b. That's the start. That's the setup in one of these questions. And the absolute max is to find out which x value between a and b gives the largest possible y value. Just literally the largest y value in the graph. So it's the tallest point, like in the picture we were looking at. Same deal for the absolute min or the global minimum. You're finding which x value between a and b gives you the smallest possible y value. So I'll pause for a moment so you can take a moment to write down as much of that as you'd like. I'm going to doodle to make sure we're still here. Okay. All right, so what I've included is, here's what we're going to do. We're going to now talk about how do we get these things. We said what they are up here, but how do we get absolute maxes and mins? And the reason we are doing this process is because next week we look at optimization. Optimization is you're given a function and you're trying to find what's the smallest possible y value of that function or the largest possible y value. Maybe you're looking for the smallest possible y value because the function represents pollution, or you're trying to maximize. You're trying to find the largest possible y value of that function because maybe the y value represents profit. The process that we look at today mainly relies on derivatives. Okay, so it's an application of derivative. And I should comment on this little warning right now is that this process we're about to look at for absolute maxes and mins does look kind of similar to finding local maxes and mins. There are some differences, and so it can be a little confusing. Therefore, I think it's important to remember today's procedure not as a bunch of steps to memorize, but it's much easier to handle what's going on in today's procedure if you just remember that derivative is slope. So please remember derivative is slope. If you remember that, I think it makes everything that we're doing fit together way nicer. So let's explore. We're only using graphs to explore right now. How do we go about finding absolute maximum? Well, to find the absolute maximum, a good place to look is local maximum. So in this picture, let's say you're given an interval AB, so you're only supposed to look at x values between A and B. So I've just labeled an A and a B, some tick marks on the x-axis, I'm trying to say, even though this function goes on beyond AB, like look at this part on the left, right? All this stuff over here, it's all part of the function in this example, but we're not looking at it. Maybe there's like a regulation from the government that X can only be between A and B, or maybe there's like a union bargaining agreement, so you can only hire this number of employees, or there's all kinds of reasons that a problem might have a restriction where X has to be between A and B. And so just generically, without looking at any specific story problem, which we'll do next week, right now we're just calling that X has to be between A and B. So only looking at this part of the graph right there, that's between X is A and X is B. If you're trying to find the global maximum, or the absolute maximum as it's also called, you're trying to find the highest peak. So if you're trying to find the highest peak, why not just look at the peaks, right? Like, why not look at any peak? So these local maximums, there are 3 of them in this picture, 3 humps. These are all good places to look for an absolute maximum, because an absolute maximum is the tallest possible point. So of these 3 local maximums, this point on the right over here is the absolute maximum. So it's a good place to look. We should look at local maximums to find absolute maximums. Here's a second picture. This slide shows another function. And in this case, to make things a little more concrete, the last one was abstract. I just said you have X values called A and B. Now I've picked literally the X value A to be the number -4, and I've picked the other X value called B to be the number 6, just to make it a little more concrete. And I'm looking at this function. Maybe this function continues on further after X equals 6, but I just didn't even draw that part, just chopped it off. And there are these peaks here, like this 1, 2, 3, 4. So there are 3 local maxes that you will find in the first quadrant, and then it looks like there's a 4th local max in the second quadrant. And this point in the second quadrant, which I highlighted, that's the global max, or the absolute max. Right, that is the tallest point. So we want that. We want the point that has the biggest Y value. And then I think here's a good opportunity to bring up the language. So 5 is the absolute max. So the Y coordinate is the value of the absolute max. And then how do you talk about the X coordinate? In this case, -2. I hope it's not too much of a surprise. We use this word at. So you can say 5 is the absolute max. You can say there's an absolute max at X equals -2. So this language, I hope it's not surprising. It sounds a lot like the language we used for local maxes. In fact, because the word at is here, even if you left off this X equals 2, just saying at, that's supposed to indicate we're talking about an X value already anyway. So language is a lot like for local maxes and mins. Okay, so far I've shown 2 pictures, 2 different functions. And from the picture, I hope you feel convinced that to find the point with literally the largest Y value, it'd be good to look at all of those, any of the peaks that we have, right? Any of the local maxes. So this is a good idea. But, so one more slide looking at pictures of functions. We got to be a little careful. So it is totally a good idea to look at local maxes. However, looking at local maxes, this is not the only place to look. Yes, definitely look at local maxes, but that's not the only place to look. So take a look at this function that's drawn here. And if you look, there's a local max right there. I'm pointing an arrow to it right now. There's another local max right there. So if you just look at the 2 local maxes, fine. But right now, the thing is, if we're supposed to look at this function between X equals A and X equals B, which are labeled on the X-axis, neither of those 2 points is the point with the largest Y value. So amongst this portion of the graph that I'm sort of highlighting right now, the largest Y value is actually found at this point right there. Right? This point on the very end, when X equals B, the Y value here, this point is taller than these other 2 points here. So I've got this, there's this point that I've pointed 2 arrows at, maybe 3 arrows at, right? That's the point we want for the absolute max. That's the largest y value because it's higher up than these other two peaks. These other two peaks over here. Those are local maxes. So the point is, local max is a good place to look, but it's not the only place to look. So we'll look at the local maxes, and then we just need to look at one other place. The point is, to find absolute maxes, here's the short version of the story. Yes, look at local maxes. However, look at another place. Also look at the endpoints. So look at x equals b and look at x equals a. You might say, why look at x equals a? Well, in this particular picture, for this function, it didn't matter, but we're about to develop a procedure that can be done without even graphing. So that's really, in a nutshell, it. To find absolute maxes, look at the local maxes, and then just see what happens at the endpoints. So here's the complete procedure. Okay, we're done exploring. If you ever forget the procedure, I want you to go back and recreate the story based on the pictures. The pictures lead to this procedure. So to find absolute max or min, when you're given a function f, and you're typically also given a closed interval a to b, then step one, check that f is continuous on that interval. This step is a technicality. I would say I don't want to emphasize this step. Not for exam 3, because this is not covered in exam 3, but for exam 4, if you didn't do step 1, I'm not even really that stressed about it. The key steps are after. So step 2, here's a key step. Find the critical numbers of f in the interval. The open interval a to b is what the book says, so I've just copied that language here. But find critical numbers. This should be fairly familiar from the past. This is where you take a derivative set equal to 0 in a nutshell. And then the third step is to find the y values, right? So find the y values at the critical numbers from step 2, but also at the endpoints x equals a and x equals b. The key thing here is to find the actual y values. So I'm trying to talk a little slower to make sure you have a chance to write. But find the actual y values, which means if we're talking about points that are in the graph of the original function f, you need to plug into f, not into f prime. It's a common error at this point for people to want to plug into f prime. Remember that f prime is a slope. But in the graph of f, not that you have to graph f, but in the graph of f, you want to know what's the largest y value and what's the smallest y value, which is why you need to plug into f. Finally, once you've plugged in the x values from step 2, as well as these two additional x values, namely x is a and x is b, you've plugged those x values all into f, then now it's time to report. So the largest y value that you see is the absolute max, and the smallest y value you see is the absolute min. I'll just pause for a moment, see if we're okay. I'll give you a little more time to write, see if we've got any general questions before examples. Okay. Some comments. I should comment first that this procedure up here looks like a lot. I think you'll actually, this is to me a much more enjoyable procedure than finding local maxes or mins. But I want to comment that to discover this procedure in the first place, we thought about the graphs. We thought about pictures. That said, when you actually perform this procedure, you don't need to draw any graphs. You don't need to do any graphing. That's what makes it kind of nice, right? So this seems to have a lot of steps to it, but I want to make sure that it's clear that I'm outlining. We use the pictures to come up with the procedure. Now we can apply the procedure without even looking at pictures. The most common error, sorry to need to repeat it here. I already talked about it by saying not f prime, but it's once you have those x values from step 2. So step 2 is you take f prime set equal to 0. Once you have done that, you're done with f prime. I comment on this because f prime is the most recent function that people have dealt with once you're done with step 2, and so it's real common for people to want to plug in those x values into f prime. But remember, f prime is a slope, And you want to know the largest actual y value, so you got to plug into f. We'll see this in an example. So the rest of class, I've got 28 minutes, and I've got 3 examples for you. So first example, find the absolute max and the absolute min of the function x cubed minus 6x squared plus 9x minus 1 on the closed interval from 0 to 5. So in other words, what this question is asking is, if you only look at x values between 0 and 5. Now, of course, this function here, there's no dividing. So this, you could technically plug in x equals 6 if it were just a math problem. But the point is, we're simulating optimization next week, where there's some restriction in the real life, like in the story problem. There's a restriction that x can only be between 0 and 5. So if you only look at x values between 0 and 5, if you only look at that portion of the graph, what's this graph's biggest y value and smallest y value? Of course, if we just were given the graph of the function, we just stare at it and like point at the tallest point. But the part of the point of this process is to say, graphing is so painful. We can. How do we use calculus to get this information? So we'll go through the steps. Again, just doing lip service to step 1. Just say that f is continuous. In this case, it's f is polynomials, f is continuous. I'm not worried about step 1. It's the other steps so step 2 and beyond. We need to answer, if you look back to the procedure, we need to answer what are the critical numbers of f. So in other words, what critical numbers are there what are the x values between 0 and 5 that count? We should find f prime. Here it is. Power rule on each term, right? 3x squared minus 12x plus 9. The minus 1, after all, differentiates to 0. So we found f prime. Set that equal to 0. It's kind of a usual story for us right now. How about solving this equation? It's a quadratic. I would like to factor out a 3 from all the terms. And then once I've factored out the 3, it's easier to notice other places where you get factoring. So that x squared minus 4x plus 3 factors as x minus 3 times x minus 1. You're going to get 2 solutions here, x equals 1 and x equals 3. So those are the critical numbers. Both x values, 1 and 3, are inside the interval from 0 to 5. Now, the third step, here's the key thing, is we find the actual y values. So that is, we take these 2 x values that we got here, 1 and 3, and also look at the x values at the endpoints. So one end is x is 0, the other end is x is 5. And we plugged in those numbers here, 1, 3, 0, 5, into f, not into f prime. I comment in red. We don't need f prime. We don't need slopes. And I showed a lot of work here. Not that you need to write this all down, but it's helpful to, for now, point out that I plugged back into the original function f. If you want to skip writing all that arithmetic, the key points are these are the y values over here. Let me circle that a little better. These y values over here, 3, -1, -1, and 19. So looking at these actual y values, we just want to now, the final step is to report on stuff and just say, what's the largest y value you see? It's really all it is, right? So don't overthink it here. The largest y value is 19. And so just to put in the language that we use, 19 is the absolute maximum. And the absolute maximum happens at x equals 5. What about the absolute minimum? Now we need to answer what's the smallest y value amongst these y values here. And you'll notice there's a tie. That can happen. So why not just the smallest y value is, of course, a -1. And so -1 is the absolute min, but it occurs twice. It's like a tie for first place. So happens when x equals 3 and happens when x equals 0. Or in other words, we have an absolute min at 3 and at 0. How do we feel about the procedure? I'll just pause, make sure, see if we have any questions. Okay, I'm going to comment that we are done with this question and we did not graph. That's the neat thing. On the next slide, I am sticking with this question. This, you see, we showed all the work on this slide. I want to, for a moment, not show all the work. Just get the highlights and then point out a couple things. So we started with the function, x cubed minus 6x, that function. We answered where was f prime equal to 0. I remind you we got x equals 1 and x equals 3. And then we found the y values, the actual y values plugging into f, not into f prime. Got to comment on that again. And here as well, like in these sub bullets here, I didn't show all the work. We did that a moment ago. And these y values, 3, -1, -1, and 19, you'll notice I just put this commentary language that we had. There's the largest value, 19, and then we had a tie for the smallest y value. And this is copied, that we had this language that 19 was the absolute max and -1 is the absolute min. And again, I already said it, but I needed a reminder in my slide just to make sure I didn't forget. We did this without graphing. Now, even though we did all this without graphing, I think it's really important to make sure that everything is clicking, that we look at a graph. Not that you have to graph. Let's just double check and clarify what's happening. So I already clicked on the link. It's in my next tab over here. So what you see in Desmos is you can click on the link later. Maybe the colors are not as clear because of using the video conferencing, but you'll find the entire graph is in blue. But we were only supposed to look at the graph for x between 0 and 5. And I asked the computer to give that in red. You'll see this curly brace. Don't worry about it too much. If you want to look at the details, it's just how the notation for this online graphing tool works. But so you see the entire graph in blue, the part of the graph that we need in red, and that's why it kind of looks like a dark kind of purpley color. So if I like turn off the part that we are going to look at in a moment, there's the entire function in blue, but that's not what we're supposed to look at. We should hide the entire function. We're only supposed to look at the portion of the function when x is between 0 and 5. So here it is, right? And I've labeled already the special points. You'll notice like right here, this point 1, 3, we had discovered when we set f prime equal to 0, one of the x values was 1, right? And that's, you see this picture is not surprising. That point that I keep highlighting, that's where the slope is 0. And that's what we expect because we set f prime equal to 0. Remember, derivative is slope. But that's this point over here, 1, 3, even though that's a local max, it's not the absolute max or the global max. The point with the biggest y value is over here where the y value is 19. Okay, for the point with the smallest y value, we recall there was a tie. Smallest y value was -1. That happened when x is 0, and that happened again when x is equal to 3. So I hope, even though you're not expected to draw a picture for these, looking at the picture helps clarify what it was that we just did. I've got 2 more questions just to practice. That's what I've got. Same procedure, just with a more complicated looking function. I'd like to find the absolute max and min of f of x equals x plus 4 over x. We'll do this on the interval from 1 to 3. So this function isn't continuous everywhere. The problem is what happens if you plug in x as 0, but fortunately the interval that we were given in the question avoids the situation of x equals 0 anyway. So at least on the interval 1 to 3, this function is continuous. Again, this talking about the function being continuous, it's a technicality, not too worried about it. The key thing to work on is we need to take a derivative and set equal to 0. Now, one term at a time, differentiating the x is not such a big deal. You might say, oh, I got to differentiate 4 over x, and I got to use the quotient rule for that. And you could, but I think it's actually much nicer to think about the 4 over x as 4 times x to the negative first. And if you were to take the derivative of that, there's my prime symbol, this would be a copy of the 4, differentiate x to the negative first as a -1 x to the negative second. And now while it's fine to write your derivative in this format, I think for what we're doing in a moment, it's actually nice to write that -2nd exponent as a +2nd exponent, but in the denominator. So here's my derivative for you. The x differentiated to a 1, and then the plus 4x to the negative first became a -4x to the negative second. I just instead wrote in the denominator x to the +2nd. So we found f prime, and we should do the usual things. We should set this equal to 0. We have an equation when we do this, and I know that for the most part I have encouraged you to just factor on the left side, but this one does not look so promising for factoring, so sometimes you gotta make an exception for that. This is one of these key situations. You've got a fraction in an equation. It is helpful to multiply by the denominator on both sides. So to multiply the left and the right side by x squared. When you do that on the left side, you need to distribute that x squared. So you have x squared minus 4 equals 0. Okay, here you can do things to both sides, like add 4 to both sides. That's a way to do this. But I'll just, now that it looks nice enough and there's no fractions, I am going to go ahead and try to go back to our usual habits of factoring. So x plus 2 times x minus 2. You're going to get two solutions from this. X equals positive 2, x equals negative 2. I tried to, sorry, this should have been on its own line. So there are these two critical numbers, plus 2 and minus 2. The problem here, the thing to be careful of is the interval we were given in the question is 1 to 3. The only x values that count in this problem are x values between 1 and 3. So even though x equals negative 2 is typically, it's normally a critical number, it's not one we're going to look at for this question. We're only looking at x values between 1 and 3. So the only critical number we're going to take with us is x equals positive 2. I put the plus sign for emphasis. So we take this one x value here of 2. We also need to look at the endpoints. And the endpoints are 1 and 3. So those x values, I had a typo noticed last section, so I've scribbled out some things. But the x values of 2, 1, and 3 right there. So we got the x value 2, which was a critical number. We have the endpoints 1 and 3. We need the actual y values. So I just drew this horizontal line. Below this horizontal line, there's no primes at all. There's no talk about derivative, which means slope. We need the actual y value. So to get f of 2, go back to the original f that I've boxed just now. 2 plus 4 over 2. So that's 2. 2 plus 2 equals 4. Yeah, that I screwed up 2 plus 2 in building the slides. That's maybe how tired I was or whatever. Don't tell. We also need the y value at the endpoint. So f of 1, plug in 1 for all the x's, and you get 1 plus 4 over 1, so that's a 5. When you plug in 3, the other endpoint, you have 3 plus 4 over 3. That one, it's actually, even without a calculator, it's nice enough to think about what this simplifies to in a decimal form. So 3 plus, 4 over 3, that's 1.3 repeating. So the whole number parts, you add the 3 and the 1, you get a 4. And then there's still the 0.3 repeating. So 4 point and then 3 repeating. This decimal version is nice because then it's much easier to compare these three y values against each other. 4, 5, and 4.3. Right now, all we got to do is report what's the largest y value, and that's going to be the 5. So the absolute max is 5. It happens at 1. Again, the at language is used for talking about the x value. In parentheses here, I start with in other words. Not that you would have to write this on exam 4. I'm just trying to connect things back to what we did at the beginning of class today, because this is new language. What the heck is its absolute max? What we're trying to say is, if you only look at x values between 1 and 3, then the biggest y value is going to be, it's going to happen when x is 1. And what was that biggest y value? That biggest y value was a 5. So that's what's trying to be communicated by saying f has an absolute max of 5 at 1. Okay. Similarly, if you compare these three y values that I just circled up there, the smallest of the y values is 4. And that smallest y value of 4, it happens when x is equal to 2. So we'll say f has an absolute min of 4 at 2. I'll just pause and see, are we okay with this example? Is there anything I can point out? Any wait, how did you do this or that? Right? So if I draw that same horizontal line from earlier, the point is we use the derivative to help find out where there's a hump or a valley, because that's a local min or max is a good place to look for an absolute min or max. But then once we know that's a good x value, we should then go back and find the actual y value. That's why we use f and not f prime. So I think, again, though we're done with the question, it's helpful to point out that we had this absolute max of 5 when x was 1 and the absolute min of 4 when x is 2 in a picture. So you can click on the link later yourself, but I have already pulled this up in my next tab. So our function, the entire function is shown in red. It's x plus 4 over x. And this is maybe surprising as a picture. Let me turn off the blue one that we're going to look at in a moment. If all you did was ignored the endpoints, it's a common error, and you just took a derivative set equal to 0, please notice that the points you would get are this one right there, right? That's where, just in the, if you just look at the picture, the derivative appears to be 0 there. In other words, horizontal tangent line, right? The slope of the tangent line is 0. Remember, derivative is slope. And you'd also discover this point here. This, you get x is positive 2, x is negative 2, and then you look at the y values 4 and negative 4, and that's it. But the issue is we're not to look at this entire red curve. The restriction given in the problem was that x should be between 1 and 3. So now let me hide. I turned on the blue one. Let me turn off the red one. And this is the only portion of the function that we are supposed to look at. So the work we did, it was, because you notice that this graph was kind of strange. It's not one I expect you to make on your own, right? Like we look at this function and go, we got the information that we're staring at in the picture without having to graph. So where's the smallest y value? It happened to be right there, was x equals 4. That happened to be a place where there was a valley, right? That's where the derivative was equal to 0. So it happened to be where there was a local min. And so a local min was a good place to see if maybe that was a global min or an absolute min. I mean, a local min is always a good candidate, but it might not always work. So same deal for absolute max or global max. It's good to look at the local maxes, but it turns out that the absolute max happened at this endpoint right over here, 1, 5. There was this other endpoint we looked at, and we just had to compute the y value here of 4.3 repeating, just in case, because we didn't graph. So all we're doing is like the step 2, I guess it was. Step 2 allows you to get the x values that matter. And then step 3 is just, okay, at each of these x values, like just find out which y value is the best, or which is the biggest, and which y value is the smallest. Okay, one more. I think because last section I had to fix the errors, I'm doing better time-wise. So one last one. If we were meeting in person, I had in my previous version of the notes written in an intention for you all to just work on it on your own, but I think a little easier if I just kind of talk through this. So we've got this, no more fractions, so this one should go a little more smoothly. I've got the function f of x equals negative x squared plus 6x minus 2. We're only to look at x values between 2 and 5. Okay, so next week, this problem might be part of a story problem, and due to government regulation or whatever, the x value should only be between 2 and 5. That's what we're simulating right now anyway. So just the step 1 is the thing not to worry about. I'm trying to de-emphasize it, but the book mentions step 1 is to say that the function is continuous. Okay, the key thing is we need to find critical numbers. In other words, we need to find those numbers that you would put on the f prime sign chart. So critical numbers of f are the sign chart numbers for f prime. So we take a look at f and then compute a derivative, right? So negative x squared differentiates to negative 2x, and then the 6x differentiates to 6. The negative 2 differentiated to a 0. So you have f prime. It's always defined, but we should also find out where is f prime equal to 0. So we set f prime equal to 0. Negative 2x plus 6 equals 0. I'll factor out a negative 2 and have negative 2 times quantity x minus 3 equals 0. When you set negative, so you've got two things multiplied together on the left. One of those is a negative 2. The other is an x minus 3. When you set negative 2 equal to 0, there is no value of x that makes that happen, so no solution. But then when you set x minus 3 equal to 0, you discover x equals 3. So that's the only solution. In other words, 3 is the only critical number. 3, by the way, happens to be an x value that is between 2 and 5, so we keep it. And so then what we now need to do is get actual y values. So at this point, we're done with f prime. I want to clarify again that above this horizontal line, we needed f prime, and we set f prime equal to 0 just to find out where does the graph level off. That's what f prime set equal to 0 gives you, right? F prime equals 0 is slope equals 0. Wherever the slope is 0, that's where you're going to see a peak or a valley. So now we're done. The point is, once we discover any special x values where there might be a peak or a valley, we're done with f prime. So when x equals 3, there's going to be probably either a peak or a valley. And we don't know which. We don't really care. It's just like wherever there's a peak or a valley, that's a good place to look for an absolute max or min. But now we need actual y values. So no f primes now, right? If you computed, I got to emphasize, if you computed f prime of 3, I can tell you right now that you're going to get 0. And I didn't bother computing it back here. You could. The point is, we just set in this arrow, this next line, we just set f prime equal to 0. And we got x equals 3. So, of course, we just answered the question, what x values are going to make f prime equal to 0 anyway? So when you find f prime of 3, of course you're going to get a 0. But I don't want the slope right now. I needed the slope to be 0 to look for local maxes and mins. Now I need actual y values. So below this horizontal line, we need actual y values, plug into f, not into f prime. So do that for the special x value 3 that we just discovered, where there might be a peak or valley. But also do this for the x values 2 and 5, which are the endpoints. So I didn't bother showing you all the work here, but I plugged in x is 3, and then plugged in x is 2, and then x is 5 into the original function up there. My y values that I got were 7, and then 6, and then 3. So what we need to do now is report on what's the largest y value, what's the smallest y value. So this is, again, if you kind of just, I know we haven't graphed it yet, but if you just kind of picture what's going on here, we need actual y values. That's why we're plugging into f. So the largest y value is 7. To use the language, though, to practice the language, f has an absolute max of 7 at 3. And I'm just commenting right here that this 3 happened to be a critical number. So the absolute max can happen at a critical number. But as far as the absolute min, the min was this y value 3 that I just circled. That y value is the smallest. And this min of 3 happened at 5. So the min in this example happened at an endpoint. So this is why it's important to check the y value at critical numbers and at endpoints. We'll show you a picture, and then I'll just repeat a couple announcements. So yeah, let me pull this up. Over here. So the entire function again is shown in red, but we are not to look at the entire function. So I'll turn that off. The relevant portion of the picture, we were just told in the question to only look for x values between 2 and 5. And yeah, there we go. So I just clicked on the point, and that point there happens to be local max, but it also happens to be the absolute max. This was the absolute max of 7 at 3. For the absolute min, the smallest y value happened to be over here. The smallest y value is 3. That happened at 5. But we didn't know because we didn't graph, so that's why to check, we also plugged in x is 2 and got the y value to be 6. It's just this y value 6. I'll go back to the slide and you'll notice this y value 6. It just didn't matter, right? 6 wasn't the winner. 6 was not the winner as far as the biggest y value or the smallest y value. It was just there. But we had to compute it. If you're not going to graph, you just had to compute to see. Okay, so I hope we're okay overall. Let me, again, I'll do some announcements and then preview what we're doing tomorrow. The announcements, again, just to go through rather quickly here is, in case people joined late, there's a quiz tomorrow, an online quiz. The format is a little different, so please turn in a picture. The reason it was text writing last week was I didn't want to assume everybody had a phone. But for a picture, so you can use a phone, or you can still just type on screen and then take a screenshot. So there's an exam Thursday, or Thursday's the official date of the exam, but because I'm trying to recognize people have different schedules, between the 48-hour period from Thursday to Friday, that the entire 2-day period, you don't get all 2 days, but somewhere in there you should schedule for yourself a 5-hour window of time is what you're given. So as soon as you hit start on the exam in any of this 48-hour period, you will be given 5 hours in which you get to see the questions and then turn and upload pictures for each of the questions. Just like for the quiz, there's a practice exam that's in this format where you can just try out the format, or you can turn in whatever. I'm just going to delete it once the exam is all done, right? So, okay. And then, yeah, the preview for tomorrow is the following, is that you'll notice what we did today. There's some similarities and some differences between finding absolute maxes and local maxes. And so these things tend to get a little confused for each other. And so tomorrow's goal is to like double check and to sort out what are the differences and what are the similarities. And I'll just punchline right now is it's easiest to keep track of everything if you just remember that that derivative is given, the derivative computes the slope. I think that's all I've got. So I will see you tomorrow. Okay, stop the recording.